So you should have learned a bit about gradient in GCSE. Y equals mx plus c. Gradient is m. We've done it as well in coordinate geometry. So we're going to have a look now at gradients, not of lines, of curves. So the gradient of a line, across one, up how much? Across one, up how much? Across one, up how much? It doesn't change.
Yeah.
It's always the same. So you can reference this thing called the gradient of the line, one thing, and it's if you go across one, how much do you go up? Across one, up n. Across one, up n. Across one, up n. Doesn't matter where you are.
Yeah.
With a curve, say I'm here, and I go across one, I go up that far. But if I'm here, and I go across one, I go up a completely different amount. And in fact, if I'm here, and I go across one, I end up going down. And if I'm here, and I go across one, I only go up a bit. And if I'm here, and I go across one, I go up so far, it's just ridiculous, I can't even draw it. So you can't say, what is the gradient of the curve? You have to say, what is the gradient of the curve at the point so-and-so? So whereas a line, you can say, what is the gradient of the line, full stop. A curve, you can say, what is the gradient of the curve at x is minus 4? What is the gradient of the curve at x is 0? What is the gradient of the curve at x is 7? But at a certain point, because the gradient keeps changing. So anything about the height of the curve, we already know we've got a function that tells us the answer. So for example, where is the height equal to 40? So where's 40? Here?
Yeah.
Oh, there's an obvious answer. X is 0. When x is 0, y is 40. The height is 40. Actually, there's another place, isn't there, right here?
Yeah.
And there's another place there. I don't know what they are. Maybe I could solve the equation. Let's say y is 40. I wonder what x is. That's the equation I need to solve. I know what y is, I don't know what x is. I could take 40 off each side. I could factorise out an x here. Does that factorise? 2, 9, 3, 6, 3 and 6?
Yeah.
Got it?
Yeah.
Okay, so either this factor is 0, 0. Oh, we had that one, didn't we? Yeah, 0. That's that one. Or this factor is 0, so x is 6. That must be that one. Or this one is 0, so x is minus 3. That must be that one. Yeah. So a question about the height of the graph is basically about y. We know what y is. What is x? Or we could equally say x is minus 1. I wonder what the height of the graph is. Yeah, so now we know not what y is, we don't know what y is, we know what x is. But we can sub in the x instead of subbing in the y. So you get minus 1 cubed, minus 3 lots of minus 1 squared, minus 18 lots of minus 1, add 40, which is something.
Yeah. Minus 1.
Minus 1, add,
3.
no, minus 3, you're right. Add 18, add 40. 54? So that's 54. So this coordinate here is minus 154.
And 54 is the height.
Yeah, 54 is the height of the graph at that point, the y coordinate corresponding to the x coordinate. So height is all about y and x, basically. And when we're talking about gradient, steepness, we need a different function because we're saying, you can't say what's the gradient, what's the steepness, you say what's the gradient at a point. So this tells us about height. It's the y coordinate. So this is the height at x. Whereas this notation, dy by dx, we call it, dy difference in y divided by difference in x. So that's the change in y over the change in x, gradient, that's how we find gradient. So this is the gradient function, and this is the gradient at x. And in the same way that obviously the height changes depending on what x is, the gradient changes depending on what x is. So we just asked what's the height when x is minus 1, and we've got 54 or something.
Yeah.
So we said x is minus 1, we found out that y was 54. If we put minus 1 in here, into the gradient function, then we get 3 times 1 is 3, add 6, minus 18, minus 9.
Yeah.
So So the gradient, dy by dx, the steepness of the graph, when x is minus 1, this steepness here is minus 9. Looks about right, it's going downhill, about minus 9. Obviously, if we put a different x in, we'd get a different gradient, because the gradient keeps changing wherever you are in the graph, in the same way as the height keeps changing. Also, we could say, where is the gradient? So, on this one, we said, where is the height 40?
Yeah.
So we knew that y was 40, so we substituted that in, and we found x. And then we said, x is minus 1, what's the height? So you can do the same thing with the gradient. We just said, I'm at minus 1, how steep is it? But we could also say, where is the steepness 0? Where is there no steepness? Like here and here. No steepness. Gradient is 0. Because it's not going down, so it's not going up. Gradient's 0. So I could ask, well, I could equally ask, where is the gradient 10? Or where is the gradient 7? Or where, I've just noticed these ones because they seem quite obvious. Where is the gradient 0? So now, I'm subbing in here.
Yeah.
The gradient needs to be 0. So then I'm solving this equation. Probably start by dividing everything by 3. And then hope I could factorise. 4, 3, 4, 2, 4, 3, 6. I don't think I can. Formula. Complete the square. Something. Solve. And then you could find out. Actually, I want to do it. I want to do it. So, x, what am I doing? 0 equals x squared minus 2x minus 6. I can't factorise it. I'm going to complete the square. 0 equals x minus 1 squared minus 7. I'm going to put the 7 on the other side. Square root. And then move the 1. Okay, so this one here must be the 1 minus root 7. And this one here must be the 1 plus root 7.
Yeah.
Isn't that difficult?
So it's just rearrange your formulas.
Yes. The point is that if I've got any sort of question about gradient, I need dy by dx function, and if I've got a question about height, or I know y and I want x, I need the y function, the height function. Obviously, we need to know where that dy by dx came from. That's the point of this particular video. So the process of getting the gradient function from the original function is called differentiation, and this is how you do it. The gradient function is, you take the power, and you're going to pull that power down and make it into a multiple instead. So instead of it being x cubed, that 3 is going to come down there. And then it's going to reduce by 1. So instead of being a 3, it'll be a 2. So now, next one, this 2 is going to go down and become a multiple. So it's going to combine with the minus 3. So what would I have there? Minus 6, exactly. So I've got minus 6. And then the power goes down by 1. What power have I got on that?
X to the 1.
X to the 1, yeah, we don't write it, but it's a 1. So the 1 comes down and times is by the minus 18. Minus 18. And then the power goes down by 1? No. Okay, what have I got here? Invisible x to the 0, exactly. I've got x to the 0. Don't bother writing it, but it's there. 0 times 40? So I don't even need to bother, no, because 0, in fact, don't even, go on, nothing. Okay, tidy it up. 3x squared minus 6x minus 18, because we don't write to the power of 0 and we don't write the power of 1. So that's how I got the gradient function. And then what we're going to do is just practice getting gradient functions. So, a couple of examples. Do you want to have a go?
Okay. Right, so I'm looking at dy by dx now.
Gradient function.
So this is going to come down and become a multiple. So I'm going to get 3 times 3, which is 9x. And then I'm going to take 1 off that power, so it becomes 2. Oh, and then this minus 1 is going to come down and become a multiple. So that's going to become minus 2 plus 2 times minus 1x. And I've got to take another 1 off that. So minus 1, take 1, minus 2.
Yep, that's right. Perfect.
Gradient function, that power comes down to x, and then I've got 2 minus 1, which is 1, which we don't really write.
No, we don't rewrite power of 1, no.
And then I've got the 1 here, that comes down, so it's 2 times 1, which is 2. X, 1 hit 1 is 0, so I don't need to write that either.
No, x to the 0 is just 1, so we don't write it.
And then all the numbers are gone.
Yeah, because you've got here an x to the 0, 0 times minus 1 is 0, so it would just be 0 on the end, so we don't bother writing it. Exactly. Okay, hopefully you've got the idea. You've got 6 to have a go at, so pause the video, have a go yourself, and just see if you can do it yourself, and then we'll go over the answers. So, first 2. We've got a v to deal with first. Did you just differentiate the top and differentiate the bottom? If so, you fell for the trick. You need to first of all sort it out so that it's in the form that we learned how to differentiate, where there's a number and an x and a power.
Right, so we have 2 over x minus 3x squared over x, which is 2x to the minus 1 minus 3x.
Yes, now we can
So
differentiate.
now dy by dx, because you're working with x beforehand, is bring down that power, just minus 2x to the minus 2, and then minus 3.
Yep, because you've got a 1 here, 1 times 3, well 1 times minus 3 is minus 3, then you get an x to the 0, but we don't bother writing x to the 0 because it's 1, so we don't bother writing it. Yep.
Roots aren't nice, particularly when I'm dealing with like indices.
Yeah, you
like
need it as a
that.
power, yeah. Yep, now you can differentiate.
Right, so we've got 3, and then we get this power down, and then we're going to take 1 from that power, so that goes to minus half.
Yep.
And then we've got 4, bring that 2 down, and x to the 1, which is
Yep.
x, and then that just needs tidying up.
Excellent. Okay, next 2. I'll have a look at these. So, not ready to differentiate yet because this needs to be written in power form. Now I can differentiate 4 times 2 is 8, decrease the power to 1, which we don't need to write. Bring the minus 1 down, minus and minus gives a plus, and decrease it by 1. 3x to the half add 2. Now it's ready to differentiate. Dy by dx is 3 times a half, 3 halves, take 1 off the power. And then here 2x to the 0, but the 0 times the 2, so don't need to bother. Last 2.
Okay, this isn't in the form we want yet. 3x to the 3 minus 2x to the half. Bring that down, that's 9x squared. Got dy by dx now. Minus 2 times a half is 1x to the minus a half. Excellent. Would that be the answer, the format they want it left
Yeah.
in? Yep,
Yeah.
so you wouldn't ever go back and do that as 9x squared minus 1 over root x?
It's a really good question. I think basically this form here is really nice if you're solving an equation. And I think if you then wanted to solve like where is the gradient equal to 2,
Yeah.
so you were trying to solve this equation, then I would write it like that. But for differentiating, you need it in the power form.
So leave it like that then.
Yeah. So when you're doing the actual calculus is differentiation and integration, which is the opposite of differentiation. You need the power form. You have to have the power form. But for equation solving, I agree with you. This is much nicer. So, for example, really good example is that sometimes students get. Let me see if I can make one up that will work. This, and then they say, right, well, I need to write it in the form, I think this will work, x to the minus 1, and now I can differentiate it, so dy by dx is minus x to the minus 2,
Yeah.
and then they have to solve, they have to find out, they know that the gradient is 4, for example, and they're trying to find out what x is, so they know the gradient is 4, and then they get totally stuck. No idea what to do at all. And for some reason, the brain is happy working in this direction,
Yeah.
but won't reverse the process. And I don't understand why, because surely if your brain knows that 1 over x is x to the minus 1, then your brain knows that x to the minus 1 is 1 over x.
You'd think.
You'd think. So you'd think that someone would be able to look at this and say, well, that's 1 over x squared, and then times both sides by x squared. Actually, this doesn't work. Sorry, I tried to make one up that would work, and it doesn't. But it's not solvable. But the point is, if we pretend that minus isn't there, just pretend it's not there for a minute. If you have 4 equals 1 over x squared, that's fairly easy to solve. 4x squared is 1, x squared is 1 over 4, x is the square root. Yeah, exactly. But that requires you to take this step, which is the opposite. Yeah, and I don't know why. I don't understand why, if you give a student 1 over x squared, they say, well, that's x to the minus 2. But if you give a student x to the minus 2, they have no idea that that's 1 over x squared. It doesn't make sense to me that the brain can know that and not know that. But, yeah. So it is a really good point. And in terms of remembering strategies, number one is it goes in both directions. So in the same way that 1 over x squared is x to the minus 2, x to the minus 2 is 1 over x squared. But the other thing is to remember is that for calculus, we want this.
Yeah.
So for differentiation, we want the index form, the power form. But for solving an equation, actually, this is much nicer to do. Okay.
So
last one, I think we're on.
So it's another v, isn't it? Y equals 2x over x squared minus 3 over x squared, which is 2x to the minus 1 minus 3x to the minus 2.
Yep, so now we can differentiate.
Minus 2x to the minus 2 plus 6x to the minus 3.
Perfect. And again, if you wanted to solve an equation, probably nicer to write it like that.
Yeah.
But you don't need to unless you're told that the gradient is 10 and, we're trying to solve it.